So basically, my independent research project was based on developing a test rig for vibration analysis of beams due to eccentric mass rotations. So basically, before going to the engineering background, let's talk about the objectives. As I told you, it was the development of the test rig, which can be used to study the transverse vibrations in flexible beams due to excitations from rotating eccentric masses. So how this project works is that several test cases is formed on the basis of beam dimensions and end conditions, and based on these test cases, sensitivity analysis will be carried out. And sensitivity analysis in the terms of, for example, amplitudes, frequencies, factor of safeties, these things will be carried out with the help of these test cases. Two types of beams are considered. I'll talk about them in detail later. First one is flexible, the second one is rigid. For the rigid beams, variation of reaction forces at the joints are calculated, and for flexible beams, the amplitude has been calculated. The ultimate purpose of this project is to conceptualize an appropriate test equipment or an apparatus which can be utilized by various labs for different purposes. So let's talk about the engineering background. The two photos you are seeing on your screen are the photos of steam turbine exhaust casings. The idea for this project came to me during my internship at Siemens Turbo Machinery, where so steam turbines are fabricated and assembled. So as you can see in these exhaust casings, there are beams which are fixed in this particular casing, and the point of these, or the purpose of these beams, is to ensure that in the exhaust casing, or the exhaust casing as a whole, does not shrink. So as we know that if you have read about steam turbines, you probably know that when steam flows from high pressure to low pressure areas, and the steam turbine exhaust casing is the low pressure area, the pressure drops below the atmospheric pressure, and the temperature is also, because of low pressure, the temperature also drops. So there is always a chance that the steam exhaust casing may shrink, and to prevent that, these beams are there. So what is the big deal in understanding, like, or how does the effect of vibration come on these beams in the first place? So let's understand the harmonic force due to eccentricity. So basically, this is a very rough illustration of the problem I'm talking about. As you can see in this particular diagram, this is a particular beam which is connected to two journal bearings, and this is the journal axis, sorry, this is the bearing axis, and this is basically the rotor. And in most of these rotors or shafts, as you know, what happens is that the center of mass is always at an offset distance from this bearing axis. And this, as you can see, this is the eccentricity of this particular center of mass. And now when this rotates at a particular speed or a particular frequency, which is omega, first of all, the first effect is obviously the whirling of the rotor, or of the rotor shaft. The second, more profound effect is the vibrations which happen in the nearby assemblage or nearby assembly. So basically, as we can see in this diagram, because this is rotating, the system is rotating, the center of mass will experience an inertial force, or basically a centrifugal force, and this will be equal to this the mass, the offset distance or the eccentricity, and the speed with which the rotor is rotating. And this inertial force is the force which is the harmonic centrifugal force, and this is the force which leads to some vibrations in the assembly which is near the rotor. So basically, as you can see again in this picture, in steam turbines, what happens is that the parts are very close to each other, and there are very minute tolerances, very high precision parts. Because the parts are very close to each other, if the rotor if the rotor leads to some kinds of vibrations, these beams which are connected to this in this exhaust casing will have to bear some vibrations, and the source of these vibrations is this inertial force. So to understand this, yeah, to understand this, we are considering the Euler-Bernoulli beam theory. So basically, in this theory, we study the effects of transverse vibrations on a continuous beam, like a continuous system like a beam. And the major assumption of this theory is that at any point in the system, if we cut out a section of the beam, that section of the beam will always be perpendicular to the neutral axis. So basically, this is the theory which we are following. And so basically, as you can see, this is the governing equation of the vibration on this particular beam. So it has two parts. It has the X dependency part and the time dependency part. This talks about this, or this gives you an idea about the normal mode of vibration. The normal mode of vibration meaning the frequency or the natural frequency or the resonant frequency with which the rotor is the beam is vibrating. And the second part, this talks about it's used the equation of motion with respect to time. So the test cases I was talking about. So because I have done two kinds of analysis, rigid beam analysis and flexible beam analysis. The primary reason for this bifurcation of analysis is due to the constraint which the student version of HyperWorks or Motion View presents. So basically, in the student version, you can't you have like we can't you make the use of flex body prep, which is used to make the flexible beam. So that's why to ensure that each and every case is taken into consideration, I had to make the use of rigid beam analysis as well as flexible beam analysis. So in the rigid beam analysis, there are 6 cases. The first 3 cases deal with changing either the thickness or the length of the beam, and the only constant part in this particular in the first 3 cases is the end conditions, which is the fixed beam. The last 3 parts talk about changing the end condition. So basically, it's the cantilever beam. This is the lying beam. I'll talk about this in detail later. And this is the simply supported beam. So these are the cases for rigid beam analysis where the reaction force variation of the fixed joints or the joints with which is the joints of the beams are calculated. This is the flexible beam analysis. Because we had software constraints, the only things which are changed are not the beam parameters, but the eccentric mass parameters. So basically, the eccentricities are changed. The mass, the eccentric mass, the value of the eccentric mass has been changed, and the speed with which, for example, the rotor is rotating is changed. So basically, this omega 1, omega 2, and omega 3, E1, E2, and E3, and M1, M2, and M3. So let's talk about model construction. So this is the rigid beam construction. As you can see, I'll show you the exploded view. So this is the table. This is the table on which these stands are there. The stands consist of 2 parts: this long part and this base. And there are basically 2 stands. This is the beam. And if you talk about the motor disc assembly, this whole assembly, which will be the source of vibrations. So as you can see, this is the motor body. This is the mount plate on which, with the help of which the motor will be mounted on this particular beam. This is the disc plate, which is connected to the output shaft of the motor. And on this disc plate lies the eccentric mass. Now, when this motor is switched on, or the motor is given power, this output shaft will rotate. And along with this disc plate will rotate, and along with the disc plate, this eccentric mass will rotate. And obviously, because this will rotate, it will lead to some kind of vibrations on this particular beam. Another important thing I need to tell you about is the joints considered in the fixed beam. As you can see, these are not the fixed beams, fixed joints which the software provides. It's planar joints. Now, the reason for using planar joints instead of fixed joints are basically the first reason is that when we use 2 fixed joints on this particular beam, what happens is that the software kinds of makes one of the joints redundant. So what that means is that the reaction force can be calculated in only one of the joints. It can be calculated in the other joint. The second thing, so obviously even if the total degree of freedom of the system is greater than equal to 0, this problem happens. So to ensure that we are able to calculate reaction forces on both the joints, what I have done is I have made the use of planar joints. Now, planar joints, what that means is that in this case, the planar joints have been oriented with respect to the z-axis. This means that this joint can move anywhere in the xy plane. Now, as you can see, these are the test points which are on this beam. So to ensure that this planar joint does not hinder the results, hinder the results or affect the results in a huge way, I calculated the position or the position with respect to time of these test points to ensure that the displacement in the xy plane is not significant. And according to my results, the position of these test points with respect to time comes out in the order of 10 to the power minus 5 or 10 to the power minus 6 millimeters. So as you can see, we can use planar joints in case for the fixed width beams. So this is the cantilever beam. Obviously, it's very simple because we have to just remove one of the stands, and we can analyze this too. Okay, so coming to the simply supported beam, as we know that in a simply supported beam, the beam lies on one hinge joint or the pin joint, which is emulated by this revolute joint, and the other end lies on a roller joint. Again, in this case, a roller joint is emulated by a planar joint, or even if we don't want to use planar joint, we can use J-prims, which are available in the software, such as the inline joint or the in-plane joint. Now this beam, so beam lying on any support. So basically in this particular case, what I have assumed that a particular beam is lying without any support. And so basically I know that this case does not hold so much of realistic actualization, or it's not so much significant realistically, but to ensure or to include the concept of 3D contacts in this project, I've made the use of this particular beam. So for this beam, there is another beam which is a reference fixed beam. So I'll not be comparing the basically the forces or the reaction forces uh, of this particular beam and this particular beam. I'll be comparing this particular beam with this particular beam, because obviously the positions of these two beams are similar. So so for obviously, because in this particular case, what I've done is I've not fixed the stand with respect to the table, because I want that when this thing vibrates, the vibration gets transmitted to these beams. So obviously, because if I fix these beams, fix these stands to this table, the vibrations will not be transmitted. So what I want to do is I unfix these and I introduce 3D contacts between this stand and this table, this stand and this table, and again between this beam and this stand, and this beam and this stand. And the various parameters I considered for 3D contacts. So basically, let's understand what parameters I have considered before before jumping to the values of those parameters. So basically, for normal force, so what I want is what I want in this particular case. So in the previous cases, I was calculating the joint reaction forces. Now in this particular cases, I don't have any joints. I need to calculate the reaction forces between this beam and this stand. Now, what does reaction force constitute? It constitutes of a frictional force between this surface and this surface, and it constitutes of a normal force between these two surfaces, between these two bodies, right? So for normal force calculation, I've made the use of impact contact model. So basically what this does is, so for example, consider this to be the beam body, consider this to be the support stand, the test rig stand, and consider this to be the natural length. Basically, right now there is no kind of break, or basically this is the natural length between these two bodies. Now what happens is when there is some sort of penetration between the both, this natural length obviously becomes smaller, and this L1 and L2, this distance is called as the penetration depth, or basically the depth, the amount of penetration which happens between these two bodies. Now the normal force is nothing but the spring. Basically these springs are assumed between these two bodies. So the force which will exist due to the springs, and there is always some kind of damping between these two. So this spring force is always equal. Obviously we know that for a simple mass spring system, the spring force is equal to kx, right, where k is the stiffness, kx is the amount of displacement. So similarly in this case, we have the contact stiffness, we have this penetration depth, and this is some kind of this is the exponential power or exponential value. uh, so basically, obviously we know that there can be there can be cases where the spring, mass spring, the mass spring system is behaving in a non-linear fashion, right? In case of a non-linear fashion, this penetration depth or the displacement is not is not linearly proportional to the force. So that's why to accommodate the cases of non-linearity, we have considered an exponential value. This is basically the damping force value, which according to which the software calculates it. And because this is the impact contact model, this is the basically the syntax which is of the of the solver, of the impact contact solver. So basically it has these many inputs. The first input is the natural length, is the distance between the penetration distance between these two bodies. This is the natural length. This is the contact stiffness. This is the exponential value. This is the maximum damping value. And this is I'll talk about this, right? So we have to import in the software. We have to import these four things: the Kc, the contact stiffness, the exponential value, the maximum damping, and this is the penetration depth at which maximum damping happens. So let's talk about the penetration depth at which maximum damping happens. This is basic nothing but the penetration depth, the amount of distance between the two bodies which are in contact, and this for this particular distance, the value of damping maximizes. So as you can see in this graph, this is the natural length at which the damping is 0, and this is the amount, this is the maximum damping penetration depth. At this point, the damping force becomes maximized. So we have talked about the normal force. Let's talk about the frictional force, right? So frictional force, there's only one model available in the software, which is the Coulomb frictional model, where the coefficient of friction between the two bodies in contact is the function of the slip velocity. So slip velocity, what I mean, there are two components. There's the friction transition velocity, and this is the friction transition velocity, right? And this is basically the curve which is followed. So as you can see, for the friction transition velocities between the two bodies, the coefficient of friction becomes equal to the static coefficient of friction, and the for the dynamic or for the friction transition velocities, the value of the coefficient of frictions become equal to the dynamic coefficient of friction. And there are four inputs required in this particular model. The inputs are this friction transition velocity, the friction transition velocity, and the values of these coefficient of friction of the static coefficient of friction and the dynamic coefficient of friction. So as you can see, these are the 3D contact parameters. Between the table and the stand, these are the values. For example, the contact stiffness is 1000 Newton per 1000 megapascals. The maximum damping coefficient is this is equal to 1. The stiffness exponent is equal to 2.1. The penetration depth is 0.1. So according to this, these are the values which are set for this particular model. It's important to understand that these values may not be the best values for depicting or simulating the 3D contact, the 3D contacts between these two bodies, but these values have come from a lot of experimentation and is near the best case. So coming to the results, so let's talk about the rigid beam. So for the first case, we have a fixed beam, length of 1000 mm, width of 30 mm, and thickness of 10 mm, and it's an aluminum. So okay, I think I forgot to mention that there will be two kinds of beams considered in terms of materials. So an aluminum beam will be considered, and a mild steel beam or a steel beam will be considered. For both the cases, for the cases of rigid beam analysis 2, and for the case of flexible beam analysis 2. So for the first type of result, we see that for the fixed beam, length of 1000 mm and width of 30 mm, thickness of 10 mm, and an aluminium beam, we get this marker force or the reaction force at the joints. We get this kind of variation where the maximum reaction force is about 12.3 Newton and the minimum reaction force is about 11.5 Newton, and the reaction force exists on these two joints. So obviously, because these two joints will have similar reaction force variations with respect to time, this can be seen as the result. For the same case, but the material has been changed to mild steel, we get this sort of graph where we get intuitively we can understand that while because mild steel is much stiffer, the variation in reaction forces will be much less. As you can see here, the maximum is about 19.8 or 19.9, and the minimum is 19.09. So it's not even greater than 1. So, and for this mild steel we are getting. So this is basically the spreadsheet in which the varying thickness has been discussed. So as you can see, for aluminium, if we keep thickness as 10 mm, or if we keep thickness as 15 mm, these are the ranges in which the reaction force comes out to be. And similarly for mild steel too, or steel beam, we get this sort of variation. Not just in terms of thickness, we can also calculate in terms of the length variations. So for example, if we have 1,000 length beam, 1,000 length beam, or 800 length beam, we can calculate this sort of ranges. And if we want to change the end conditions, if we want to have fixed beam or a cantilever beam or a simply supported beam, we get these sorts of ranges. So as you can see, for the rigid beams, the ranges in the reaction force values in the joints have been calculated, and depending on the varying thickness or the length or the end conditions, results have been formulated. Okay, yeah. So coming to the last case in this particular in the rigid beam analysis, we have the line beam where the length is 1,000 mm, the width is 30 mm, and the thickness is 10 mm, and the beam is aluminium. So this is sort of the kind of variation which is there in the marker force. This region, I'll talk to you about this region very soon enough. Uh, and this is the reference fixed beam. So we can compare these two graphs and to understand that to understand what kind of if there is a lying beam with a 3D contact, what kind of reaction force changes or the reaction force changes there. So let's see this lying beam animation, and this animation or this simulation has been done after introducing the 3D contact parameters I talked about. So this simulation time is 5 seconds. So as you can see, for the first 1.2 seconds, the beam was not stable. The line beam, which is lying on the test stand, was not stable. And this happens basically due to imperfect 3D contact parameters. It happens due to imperfect, so for example, imperfect damping coefficients. It happens due to imperfect contact stiffnesses. And this, this is kind of the best, it's not, although I understand this is not the most accurate, but still for the majority of the simulation time, for 3.8 seconds of the simulation time, we are getting a stable beam, and that is enough for getting results. So as I talked to you about this region, right, this region is that region where the beam is not stabilized. After stabilizing, this is the reaction force variation in the particular beam. Okay, coming to the flexible beam analysis. So flexible beam analysis, the parameters which are calculated are the beam maximum amplitude, the timestamp of the maximum frequency, the maximum von Mises stress, which is nothing but the distortion strain energy per unit volume in the beam for a simulation time of 5 seconds, the factor of safety. So basically, factor of safety means that in that particular period of 5 seconds, the value which we'll get as the maximum von Mises stresses, that will help us in calculating the factor of safety by this formula: the yield strength of the beam by the beam material by the maximum von Mises stress. And we'll be calculating the fatigue life in terms of the number of cycles for each beam material. Now understand that the first 4 parameters have been calculated with the help of software. It has been calculated with the help of the software, but the last parameter, the fatigue life, because the software does not allow or does not provide for any exclusive fatigue life calculation solver, that's why the fatigue life has been calculated for this project. It has been calculated analytically, and I'll talk about that later. So the first 2 parameters have been calculated by extracting the plot data from hypergraph to a spreadsheet. As we know that we can basically plot the plot the displacement or the amplitude of a flexible body or on the hypergraph on this particular graphing software. and we can extract the data onto a spreadsheet. So I'll talk to you about, let me just jump from this presentation and I'll show you this. So basically, this is the data I'm talking about. This is the graph data I'm talking about. So these are the times, these are the simulation or the time steps, simulation time steps. This is the reading which the graph showed, or this is the basically the flex body displacement according to the time. So basically, to calculate the maximum amplitude, what I've done is I've taken the maxima, in this particular data, I've taken the maximum value and I've taken the minimum value, and I have taken the half of those values. So basically, the maximum value plus the minimum value. The maximum value plus the minimum value divided by 2. So this gives us the maximum amplitude that we are getting for a particular case. To calculate the maximum frequency time step, we have calculated the differences which exist from if a flexible body goes from one location to another, and there's a particular Excel formula to calculate the maximum, to calculate the location of this maximum displacement. So basically, to calculate the maximum frequency, an assumption has been made that the frequency can be treated as speed. So if it is treated as speed, it just means that the maximum amount of distance that a flex body covers in a particular time step. So, but if we know that because this is a discrete distribution, the time step will be equal, and it's equal to 0.01. And if we calculate the location or the time step at which there is a maximum displacement, we can calculate the time step at which the maximum frequency is happening. And according to this, for each and every beam case, I have calculated the maximum time frequency time step. So coming back to this rest of the results, we have the von Mises stress has been calculated in Hyperview by using the contour plots feature, and fatigue analysis is done analytically with the help of SN curves. So coming to the flexible beam construction, so basically, as you can see, it's a flex body prep. It's a beam made with the help of flex body prep, and so basically, two beams have been made, one aluminum and one mild steel. And as we know that there will be three bolt conditions or three boltings on this particular beam. There will be a fixed joint on this side, there will be a fixed joint on the other end, and there will be a mount plate which is connected or mounted or fixed to this particular beam. So we have the use of three RBE2 spiders, which are nothing but the interface nodes, which are nothing but this like the rigid elements which are created at the interface node locations. Now, what does these RBE2 spiders do? What they do is they introduce infinite stiffness in these locations, and with the help of this infinite stiffness, we can emulate the conditions of a bolt or a fixed connection. So that's why in this particular mount plate location, and on these two ends, the use of RBE2 spiders have been made. And these are the node IDs, basically the node in the finite element model. These are the node IDs where the RB2 spiders are created. Now let's understand that something that in this project, a huge assumption, or not an assumption, but to simplify this project or simplify the model building of this project, what has been done is that a single RB2 spider has been introduced here. So basically, if we understand that a mount plate will be bolted or will be fixed to the beam at 4 locations. There will be 4 locations in which a pin or a screw goes in, right? But in that particular case, what happens is that we'll need to make use of something called RB2 stitching, where we make RBE2 spiders at all those 4 bolting locations of the mount plate, and then we try to connect or stitch these RB2 locations or RB2 spiders. Now, since there was lack of time, there was lack of expertise. That's why, to simplify the model building, a single RB2 spider has been made here. So the first case we can see is for an aluminium beam, and this is the flex body plot, and this basically measures the maximum amplitude of this particular beam. And this is the plot from which the data was extracted into the Excel sheet, which I showed you. Right. So basically, as we can see, when we start the motor, there is obviously a kind of a jerking action of the motor, and due to that jerking action, there's an increase in amplitude, and then it kind of stabilizes, and this is the kind of trend we get for the amplitude. In case of we can see the contour plot here. So basically, the von Mises stress has been calculated, and intuitively, the maximum stress happens at either the fixed joints or the mount plate locations. And this is the contour graph which is there for the aluminum. For the mild steel case, this is the plot which is obtained. Again, there is some excitation due to the jerking action of the motor beginning, and then there is again some jerk, this increase in amplitude, and this is kind of the plot for the amplitude which we get. So this is again the contour plot for the mild steel case, and again at the fixed joint locations and at the, near the mount plate, we get the maximum von Mises stress. So I'll show you the result sheet for this flexible beam. So yeah, so so for varying eccentricity, as I said, I varied the eccentricities, and I varied the eccentricities, I varied the mass, and I varied the angular velocity. So for varying eccentricity for 25 mm, for 15 mm, 10 mm, this is the amplitude which was calculated in millimeters, and this is the maximum amplitude. So as I showed you in the particular Excel, in the other Excel sheet, how the maximum amplitude was calculated. These are the values which were calculated, and this is the maximum von Mises stress for transient simulation. This comes from the software, the contour plots, and this is and these are these von Mises stresses change according to varying eccentricity, and this is the timestamp of maximum frequency. And this is the yield strength, and this is the ultimate tensile strength, and this is the factor of safety. Now let's, as you can see, the factor of safeties kind of do not look realistic because they are in the order of 20s, 70s. So the reason for this is that the dimensions of this model have been are kind of minute. So the dimensions, as you can see, were 1000 mm, which is equal to 1 meter. The thickness was equal to 10 mm in some cases, which is very small. So what can be done if we want to build this model realistically? We can easily scale the dimensions, but the trends which occur here will be the same, even in the case of a scaled even in the case of a scaled model. So coming to the varying mass, we have we vary the mass, and we, according to the varying masses, we check the amplitudes which are at the maximum amplitudes of the beams. We check the von Mises maximum von Mises stress, and we calculate the factor of safety. And similarly for the varying eccentric masses, varying angular velocity of the eccentric mass, we do some same kind of analysis. So yeah, so this is basically the flexible body analysis, and this is a kind of the flexible beam animation which you can see. As you can see, this is rotating at a particular speed, and this is the vibrations which are happening, and with the vibrations you can see the contour changing, the contour plot of the stress is changing. So yeah, so coming to the fatigue analysis, the last part of this project. So fatigue analysis, because as I said that this software does not provide any exclusive fatigue analysis solver, that is why the use of SN curves, the concept of SN curves has been used to calculate the factor of safety, the fatigue life of a particular material and analytically. So as you can see, let's understand this. This is the SN curve for a steel or a mild steel, and this is the SN curve for for an aluminum alloy, right? So as you can see, this basically gives us the stress amplitude, and this is the number of cycles. And this SN curves usually work in the high fatigue cycle paradigm, which means that if the number of cycles is greater than 1000, we can use SN curves. So as you can see in the steel curve, there is, after a particular location, which is corresponding nearly to 10 to the power 6 cycles, the graph becomes flat. What this means? This means that at this particular location, the corresponding stress amplitude is the endurance limit or the endurance strength, or sometimes people call it the fatigue limit or the fatigue strength, right? So what does it means that any amount of stress below this endurance limit, if it is applied to this particular material, the material will never fail. So as you can see, because this graph is flat, the plot is flat, this number of cycles tend to infinity. So basically, if I apply a stress amplitude of about 200 megapascals, the material will never fail. It will keep on like whatever amount of loading and unloading, whatever amount of frequency you apply to it, it will never fail. And this usually happens to the materials which have some amount of ferrous, some amount of iron in it. So basically for ferrous compounds. What about the non-ferrous compounds? Non-ferrous compounds like aluminum, right? For them, theoretically, no such endurance limit exists. But for calculating the SN curves, for calculating the fatigue life, what we assume is that at number of cycles equal to 5 into 10 raised to the power 8 cycles, the endurance limit happens. So based on this assumption, the following calculations have been made. So this is the governing equation of the SN curves, where this is the SN value, the stress value, and this is A, it's a parameter which has to be calculated. This is another parameter B which has to be calculated, and this is the number of cycles. So our aim is to calculate the number of cycles. We know the mean stress which is being applied. And what does this mean stress mean? This mean stress, basically, what does fatigue mean? Fatigue means that a material is being for example, sort of loading and unloading, continuous loading and unloading on a material is being done, and under that case the material becomes susceptible to fatigue. So that the mean stress of that particular loading, the maximum stress, and unloading, the minimum stress, the mean stress of that particular stress range is taken as the SN. And so our aim is we know this value, we have to calculate these, and we have based on these we have to calculate the cycle for both the aluminum beam and the mild steel beam. So as we can see, this is the endurance strength. If we have to calculate the endurance strength, this usually this SE slash or the SE dot. What this means is that this is the endurance strength of an aluminum or a mild steel specimen. So it does not refer to the actual beam or actual object on which we are carrying out fatigue analysis. It refers to a specimen of aluminum or a mild steel. Now, to convert this specimen endurance strength to the endurance strength of the actual object or the actual beam, we have to take certain factors into consideration. These are the surface condition modification factor, the size modification factor, the load modification factor. This is the temperature modification factor. These are all factors I'll be talking to you about a little while later, and how they are calculated. So let me jump into the fatigue analysis sheet for this. So so as you can see, for aluminum, the ultimate strength is about 228 megapascal. For mild steel is about 841 megapascal. And this is calculated with the help, as I showed you in the formula. The specimen endurance strength is 0.4, the value of the ultimate strength. And for mild steel, it's 0.5, the value of ultimate strength. Now, we have to calculate these factors, the Ka, Kb, Kc, and Kd, Ke, and Kf. So I'll show you how this is calculated in this project. So the first, coming to the surface modification factor. So the surface modification factor is given by this formula, where the A and B are parameters, and SUT is the ultimate tensile strength. So assuming that the beams, the aluminum beam and the mild steel beam have been forged, and these are forged materials, the values of A and B, these are the pre-existing experimental values, and using these values, I can calculate the value of Ka for both aluminum and mild steel, right? So for aluminum, it's about 1.23, and for mild steel, it's about 3.34. Yeah, and for size modification factor, we have this formula. So it's basically Kb And in this particular formula, the D refers to the equivalent diameter. Now, what does equivalent diameter mean? Since our beam cross section is a rectangular cross section, it has a particular height, it has a particular thickness, width, and it has a particular length. Right. To convert that rectangular cross section into an equivalent diameter, we have to use this formula. Again, this formula is a theoretical formula, and using this formula, we have the value of B, we have the value of H, we get the value of D, and using the value of D, we can calculate the value of KB. So for accordingly, we calculate the value of KB, and yeah, so for the value for this particular for both the aluminum and mild steel, since their cross sections will remain constant, the size modification factor is about 1.07, 1.067. Coming to the loading factor, obviously, because we assume that there will be nothing but bending loads on the beams, so the loading factor for them is 1. The temperature factor is, if it's done in room temperature, assuming that the labs exist in room temperature, or the apparatus performs in room temperature, the temperature factor is 1. The reliability factor, so basically this refers to the reliability of the particular kind of conversion from specimen endurance strength to the actual object endurance strength, and this is taken as a 90% reliability. And for that particular 90% value, we have the value of this factor as 0.897. For the stress concentration factor, so what does stress concentration factor means? So basically, in this particular project, I have assumed that there is no sensitivity notches, and assuming that the stress concentration factor is taken as 1. What does no sensitivity to notches means? The notches refers to any kind of irregularity, or any kind of holes, any kind of any kind of valleys in the beam material, or the material which we are considering. And because obviously, because due to the existence of these notches, there can be increased in concentration of stress, and because of increased concentration of stress, there can be reduced fatigue life. So in this project, to keep things simple, I have assumed that obviously, first of all, the beams will never not have so much irregularity in their structure. Secondly, even if they have irregularity, they'll not be like the stress concentration in their body, in the whole body of the beam, will not be affected as much. Therefore, assuming no sensitivity to notches, the value of this factor is kept as 1, and keeping these values, we can calculate the endurance strength at the critical location. So basically, this refers to the endurance strength of the particular beam at the critical locations. Critical locations refers to the points where the maximum load is being applied, or the points where there is a lot of notches or something, right? So at these critical locations, this is the value of the endurance strength. So this, as I talked to you about, this is the formula which we'll be using, and we have to like kind of derive two boundary conditions to find out the value of A and B. So the first boundary condition for me in this particular case is that at the value of 10 raised to power 6 for mild steel, the value of this Sn will be equal to the endurance strength. As I discussed earlier, for metals, at the value of the cycles at 10 raised to power 6, we assume that the endurance strength is achieved. So this is the first boundary conditions. On the other hand, for aluminium, instead of 10 raised to power 6, we assume 5 into 10 raised to power 8 cycles, and according to that, at that particular value, Sn is equal to this value, right? Sn is equal to the endurance strength. Now, the second boundary condition which we assume is at the beginning of the cycle. The beginning of the cycle begins at n is equal to 10 raised to power 3. And at 10 raised to power 3, n is equal to 10 raised to power 3, the value of Sn is taken as 0.9 times the ultimate strength. Now, again, this is a theoretical concept, it's a theoretical assumption, and this constitutes the second boundary condition. And according to this, so as you can see, these are the two boundary conditions for mild steel, and these are the two boundary conditions for aluminium. So according to these boundary conditions, I have these particular formulas which have been calculated analytically, for A and B, and according to that, I have the value of Sn. So basically, what is Sn? Is nothing but the it's nothing but the amount of von Mises stress which is being applied on the nothing but the von Mises stress, the mean von Mises stress which is applied on the particular beam. And again, this is if we have the value of A from this boundary condition, and we have value of B from these boundary conditions, right? So based on this, these are the results. So for case one, so which had a particular value of the eccentricity, mass, and the the speed at which the eccentric mass is rotating. So for the mean stress was coming out as 2.896, and according to the formula, according to this formula, the number of cycles is coming out in terms of in the order of 10 is to 40, and it's about 1.2 it's about 2 into 10 is to 40 cycles. For mild steel, again using the same formula and using the mean stress from the mean von Mises stress, we have this number of cycles. So for each case, we can calculate this according to the varying mean stress, and we can generate the SN curves for the aluminum beam and the mild steel beam. So the SN curve for the aluminum beam has this kind of trend where this is the number of cycles to failure, and this is the mean stress amplitude, or the mean von Mises stress amplitude which is generated. For the mild steel case, it's again this same sort of graph, and these are the two graphs which are obtained from the mild steel and aluminum beam. So that's it for my presentation project.